Hello and welcome to lecture 29. This is NPTEL online certification course on aero engine gas turbine cycles. We have started discussing about the turbofan engine configuration. In last lecture, we were discussing about the forward fan unmixed two spool engine configuration, in which fan and low pressure compressor they are on one shaft. And we have discussed about say the parameter or the important process what we mean by bleeding of the air. Then we have discussed how do we do the calculation for the cycle parameters and how to do the calculation for the performance parameters for such kind of engine configuration. So, let us take a numerical here. So, we have two spool turbofan engine which is at its preliminary design stage. The data available are say flight condition, it is at the sea level, and the atmospheric pressure and temperature are 101.325 kilopascal and 288.15 Kelvin. Fan pressure ratio is 1.36, LP compressor pressure ratio is 2.47, HP compressor pressure ratio is 12, bypass ratio is 9, turbine entry temperature or turbine inlet temperature is 1600 Kelvin, total pressure loss in combustion chamber is 3%, the heating value of the fuel is 43,000 kilojoule per kg, core engine mass flow rate is 138 kg per second. The isentropic efficiencies for different component which are assumed to be say for diffuser it is 98%, for fan 90%, for compressors 87%, combustion chamber efficiency is 96%, turbine efficiency 94%, nozzle efficiency is 95%, the Cp value and gamma value for air as well as hot gas they are given. We need to estimate the exit velocity from both core as well as fan nozzle, thrust specific fuel consumption, thermal efficiency, propulsive efficiency and overall efficiency for this cycle. So, here we need to be very careful in terms of understanding what all information it is given. Okay. Based on that, we need to start putting very first as say this TS diagram. So, let us try to understand how do we solve this numerical. So, very first thing what we will be doing is we will be putting all our components, and for those components what all informations are available to us. Say for intake, we know what is our diffuser efficiency, we know what is our temperature and pressure at the entry, Mach number is 0 since it is a ground condition. So, that is what will be helpful in calculating what will be the exit pressure and temperature from the intake. The next component we have is our fan. For fan, say fan efficiency and fan pressure ratio they are given. Based on that, we can calculate what will be the exit temperature and exit pressure from the fan. We have our LP compressor. For this LP compressor, we know efficiency as well as the compression ratio. From that, we can calculate what will be the exit temperature and exit pressure from the LP compressor. Since it is a two spool configuration, we have our HP compressor also. For this HP compressor, we know what is our efficiency and compression ratio. From that, we can calculate what will be our exit pressure and exit temperature from the HP compressor. Next component we have is our combustion chamber. For this combustion chamber, the combustion chamber efficiency is given, total pressure drop is given, calorific value of the fuel is given, turbine entry temperature is given. That is what will be helping us in order to calculate what will be my fuel air ratio and exit pressure from the combustion chamber. Next component we have is our HP turbine. For this HP turbine, we are given with the values of turbine entry temperature and turbine efficiency. Based on my work balance between HP turbine and HP compressor, we can calculate what will be my exit temperature. By using our definition for the efficiency, we can calculate what will be the exit pressure from the HP turbine. Similarly, for the LP turbine, we are having the information about the efficiency, and based on the previous calculation for the temperature, we can calculate what will be the exit temperature from the LP turbine, and based on the efficiency formulation, we can calculate what will be the exit pressure from the LP turbine. Here in this case, we have suppose a tailpipe. For that, we can calculate what will be our exit temperature and pressure from the tailpipe. We have our turbine nozzle. For this turbine nozzle, the efficiency it is given. We will do calculation for critical pressure, then we will compare and check whether this nozzle is choke or unchoke. Based on that, we will be calculating our static pressure and static temperature. Once we know what is our static temperature, we can calculate what will be the exit velocity from the turbine nozzle. Similarly, we have second nozzle, it is fan nozzle. For fan nozzle also we will be doing our calculation for the critical pressure, and by comparing we will try to identify what will be the exit pressure and exit temperature. That is what will be giving us the value for the exit velocity from the fan nozzle. Once we have all this information available with us, we will be doing our calculation for the performance parameters. Okay. So, this is how we will be proceeding with. So, let us start with the very first component here. So, as I told, very first thing you need to do is you make a practice of making the line diagram. First, make the line diagram like this. Here no information it is given. So, that is the reason, since it is LP turbine and HP turbine what we have. So, we have this as a two spool configuration. Since we have discussed this cycle where my compressor, LP compressor and fan, they are being rotated by LP turbine, that is the reason we are putting this as line diagram, but you need to be very careful, is it mentioned or not. If it is not mentioned, then you can move forward with what all you want to assume with. So, be careful. Okay. And this is representing our TS diagram. So, let us start with the first component. Our first component is intake or say inlet. Since it is a ground condition, so my M infinity will be 0. So, V infinity also will be 0. We will be doing the calculation for the exit total pressure, that is a function of Mach number and diffuser efficiency. Since my Mach number is 0, that is the reason why our exit pressure will be 101.325 kilopascal. Same way we can do our calculation for the temperature. The exit temperature we are correlating in terms of Mach number. So, here in this case, this exit temperature from the intake, that will be same as what is given, it is 288.15 Kelvin. Now, our next component is fan. So, for fan we are given with the fan pressure ratio of 1.36. So, based on that we can calculate what will be the outlet pressure from the fan. It is coming as 137.80 kilopascal. We have our efficiency known to us. We also know what is our pressure ratio for the fan. Based on that, we will try to calculate what will be the exit temperature. So, here in this case, if we will put the number as 288.15 and the fan pressure ratio to be 1.36, efficiency to be 90%, then the exit temperature is 317.55 Kelvin. Okay. Now, the next component what we have is our LP compressor. For LP compressor, pressure ratio is given, it is 2.47. So, based on that we can calculate the exit pressure from the LP compressor, it is 340.37 kilopascal. Same way, based on our temperature relation, we can say my temperature ratio, it is a function of pressure ratio and the efficiency. Since the pressure ratio and efficiency they are known to us, we can do the calculation for LP compressor exit temperature. If we will put the number as say compression ratio of 2.47 and efficiency to be 87%, the exit temperature is coming 425.15 Kelvin. Okay. Now, let us move towards the next, it is my HP compressor. I am sure you are confident enough to do the calculation for that part. Let us move there. Suppose if I consider for HP compressor, this pressure ratio is given, that pressure ratio is say 12. If I will be putting my pressure at the entry of my HP compressor to be 340.37, we will get the exit pressure to be 4084.44 kilopascal. Similarly, we can do our calculation for the temperature ratio. Here, since the pressure ratio for the HP compressor is given, that is 12, and the efficiency also is given, it is 87%, we can do our calculation for the exit temperature from the HP compressor, and this exit temperature is coming 930.41 Kelvin. Now, you may be having questions say like how exactly these pressure ratios they are being selected with, how to decide this overall pressure ratio. So, if you go through all lectures what all we have discussed in last 5 weeks, that is what will be giving you indication for that. You need to be very careful here, say this temperature at the exit of my all compressor stage or at the entry of my combustion chamber, that is what will make the sense here. It should not be same as say my turbine entry temperature. That is what will be violating our law of thermodynamics. Be careful about that understanding. Okay. So, when we are discussing about the effect of different parameters on the performance parameters, that time we will discuss this point again. Okay. But be careful. So, these numbers what we are getting, it is not the straight number. These numbers they are having their own meaning. Okay. So, next component what we have is our combustion chamber. For this combustion chamber, it says there is a drop of 3%. So, this 3% if we are putting, it is 0.97 into pressure of 4084.44 kilopascal. It says my exit pressure is coming 3961.91 kilopascal. Now, for this combustion chamber, here in this case nothing it is mentioned in terms of bleed air. So, be careful, do not get excited and assume some number. Until and unless it is mentioned, do not try to take these numbers, otherwise you will be coming out with say wrong numbers. Okay, nothing it is mentioned in terms of bleeding. So, just do the straight calculation. So, here this is representing my mass balance, it is M, this we say it is my M core, here it is MF, and here this is M core plus M infinity. Okay. Now, let us look at here. Here in this case, if we will be putting our energy balance, this energy balance it is represented in terms of say m dot core into H04 plus this is my input energy and this is representing exit, it is m dot core plus mf into H05. If we will be putting the equation, that will be giving us the fuel air ratio to be 0.0228. Okay. Now, let us move with the next component we have is our HP turbine. So, this HP turbine, it is used to rotate the HP compressor only, and that is the reason why we are writing our work balance. This work balance, it is given by m dot core Cp T04 minus T03, that is my compressor work. That is what is equal to m dot core into 1 plus F Cp T05 minus T06. Okay. So, let us put this equation, that is what will be giving us the exit temperature from the HP turbine, and this number, it is coming 1167.16 Kelvin. Now, we know in order to calculate our pressure ratio, we have correlation in terms of isentropic efficiency. So, let us put the isentropic efficiency correlation. We can represent that in terms of the expansion ratio. Since my efficiency is given 94%, my turbine entry temperature is 1600 Kelvin. So, that is what will be giving us the exit pressure to be 1008.94 kilopascal. Okay. Now, let us move towards the next component. Our next component, that is what is say LP turbine. Say for this LP turbine, now we need to be very careful here. Again and again I am telling what configuration is given, accordingly your work balance equation will be changing. Here we are discussing our fan and LP compressor that will be rotated by say LP turbine, and that is the reason why my work balance will be work consumed by fan plus work consumed by my LP compressor, that is what will be equal to work developed by my LP turbine. So, let us try to put this formula. It says 1 plus beta Cp T010 minus T02. This is representing my LP compressor work, and this is representing my LP turbine work. Be careful, again if it is not mentioned, there is something about the bleeding, do not try to put that bleed equation, otherwise the answers will go wrong. So, if this is the case, we can do our calculation for the exit temperature from the LP turbine, and it is coming to be 823.12 Kelvin. Okay. And based on our efficiency formulation, we can calculate what will be the exit pressure from the LP turbine. So, here in this case efficiency is given, that is 94%. Be careful, gamma value for the hot gas is given 1.33. So, take that carefully, do not go straight way by taking this gamma to be 1.4 for the air. In second week we have discussed what we mean by Cp value to be 1.4 and what we mean by Cp value to be 1.3 or 1.33. This is basically based on say my Cp value, it is a function of temperature, and with rise of temperature we will be having dissociation, that is what will be happening, and that is what will be changing the species contained, and this species contained, if we will be doing the calculation based on Janaf table, that is what will be giving you this gamma value to be different. So, do not forget that part. If that is the case, we can calculate our exit pressure from the turbine, and this exit pressure is 2 to 1.46 kilopascal. Okay. Now, here it is nothing, it is given in terms of our tailpipe. That is the reason why we will not consider any drop of pressure in tailpipe. Be careful. If it is not given, just remove it. Do not try to assume that part, otherwise you may come up with some wrong numbers. Okay. So, we have our straight component, that is what is turbine nozzle. For that turbine nozzle, we can take the critical pressure ratio to be P08 by Pc, and that is what is a function of my nozzle efficiency. Nozzle efficiency is given, that is 0.95, 95%. So, if we will be putting this number, critical pressure, that is coming as 115.54. Now, this we will be comparing with our atmospheric pressure, and it says that is coming greater than the atmospheric pressure. So, this is the indication that our turbine nozzle is a choke nozzle. So, our exit pressure, that is what will be the critical pressure, and that number is 115.54 kilopascal. Now, let us look at the next calculation. This next calculation is for, say, static exit temperature. This static exit temperature for the choke condition we are writing in terms of gamma plus 1 by 2. Based on that, we can calculate our exit temperature. This exit temperature is 706.54 Kelvin. Now, this temperature we will be using for the calculation of turbine nozzle exit velocity. It is gamma RT9. In this case, we will be putting these numbers, and it says turbine nozzle exit velocity is 519.32 meter per second. Okay. Similarly, we will be doing our calculation for the fan nozzle, and for fan we will be writing the critical pressure ratio as P010 divided by Pc, and here this efficiency for the fan nozzle also is say 95%. It may be possible that for both the nozzles efficiency will be different number. So, you need to select this number accordingly. One more observation, be careful here in this case, this air, it is it is not at the high temperature where my Cp value will be 1.4, that will not be 1.33. So, be careful in terms of doing this calculation. So, that is the reason why here it is written as gamma, and in previous calculation it is written as gamma suffix h. Okay. So, please do not make any mistake here, otherwise your critical pressure calculation that will be wrong. It may be possible that your nozzle will come say choke or unchoke, but rather by this calculation you will come up with the wrong value, and if my exit pressure is wrong, that is what will lead to give all values in terms of performance parameter calculation will go wrong. Okay. So, whenever you are doing this numerical, it is advisable you just take your pen, paper and calculator along with and do practice for these numericals. Okay. And this will give the critical pressure here as 70.15 kilopascal. Here in this case you can say this pressure is lower than that of our atmospheric pressure of 101.325 kilopascal. That is the reason why this nozzle it is unchoked nozzle, and we can say our exit pressure to be 101.325 kilopascal. Okay. Now, we will be doing our calculation for the temperature ratio. Here again be careful about the temperature ratio calculation, and if we are doing this calculation, the exit temperature is coming 290.84 Kelvin, and we will be having our exit velocity formulation that will be different from the choke condition. Be careful, this also we have discussed in week 2. So, just revisit that part in order to build the confidence. Here this if we are putting, it says our exit velocity is coming to be 225.83 meter per second. Now, since we have our exit velocity numbers available with us, the very next will be in terms of calculation of the performance parameters. So, performance parameter, very first parameter we have is our thrust, and we know this thrust it is comprising of hot thrust and cold thrust. Both for hot thrust and cold thrust we are interested in momentum thrust, momentum drag as well as pressure thrust. Now, in order to calculate our pressure thrust, we must know what will be the area at the exit of my nozzle. Okay. So, let us try to put this in terms of calculation. here we can write down this formula. So, for say turbine nozzle, our requirement is in terms of calculating what will be the area, okay, what will be the exit area of the turbine nozzle. That is what we can write down in terms of my density and my pressure. So, density calculation if we are doing, it is coming 0.569 kg per meter cube. If we will be putting that in the mass flow rate equation, we will be having our area to be 0.477 meter square. So, this is the exit area of turbine nozzle. Same way, if we are interested in calculating the exit area of the fan nozzle, and for that we are not aware of what is the fan mass flow rate. So, based on bypass ratio we can do this calculation, and this is coming to be 1242 kg per second. Okay. Now, let us put that for the equation for area calculation, and this A11 that is given by m dot f divided by V11 into density at the 11th station. So, this density we can calculate based on pressure and temperature. Since these numbers are known to us, it is coming to be 1.214 kg per meter cube. If we will put this in the area equation, then it says the exit area is coming 4.53 meter square. Okay. Now, since our area also they are known to us, so that is what we will be putting in our thrust equation. So, let us try to write down the thrust equation. This is the thrust equation for the cold thrust, and this equation it is for the hot thrust. Now, we have all our numbers available with us. So, we will try to put those numbers. By putting those numbers, our net thrust is coming 360.56 kilonewton. Okay. Now, next we want to calculate our thrust specific fuel consumption. This thrust specific fuel consumption, it is F into m dot core divided by thrust, and this if we will be doing, it says my thrust specific fuel consumption is coming to be 0.0087 gram per Newton second. Okay. Now, after doing this calculation, we are interested in the calculation for the efficiency. So, this efficiency we have is propulsive efficiency. So, this propulsive efficiency formula, now you are thorough with what will be the equation. So, just try to remember one equation for the turbojet engine, and in place of your thrust you can put two separate thrusts like thrust of hot stream plus thrust of cold stream. Same way you need to put one more equation in terms of 1/2 mv square, that is for the fan. Okay. So, if we are putting here, it says my V infinity is 0, that is the reason our propulsive efficiency will go 0. Similarly, we can do our calculation for the thermal efficiency. In this thermal efficiency, we know what is the mass flow rate of the fuel and the calorific value of the fuel. So, if we will be putting this number, it says thermal efficiency is coming to be 37.48%. Be careful what all units we are using, that need to be in joule per second, okay, joule per kg. Okay. Now, next what we have is our overall efficiency. This overall efficiency we are calculating based on propulsive efficiency and thermal efficiency. Again and again, this is also known as thermopropulsive efficiency. Since my propulsive efficiency is 0, so our overall efficiency will go 0. So, let us try to put all this together. What we have is our ground condition, where my V infinity is 0, my atmospheric pressure and temperature they are known to us. We have done the calculation for the area of the nozzle at the exit for turbine nozzle as well as for the fan nozzle. We have done our calculation for the net thrust, this is 360.56 kilonewton. The thrust specific fuel consumption is 0.0087 gram per Newton second. Our propulsive efficiency is going 0 because my V infinity is 0, and thermal efficiency is coming to be 37.48%, and overall efficiency is going 0 here. So, here we are stopping with what all calculation we have done. We will try to discuss the effect of different cycle parameters on the performance of our engine, or say performance parameters. That is what will be giving us idea how the numbers for those cycle analysis, or say pressure ratio, temperature, all those parameters they have been selected for design calculation, for the optimization. Thank you very much.